All right. So tree diagrams, tables, and sample spaces. Section 10.4. When we get done with this section, we will hopefully be able to construct tree diagrams and use them to determine the sample spaces and compute various probabilities. And also use tables to find sample spaces and compute probabilities. So tree diagrams or tables are all useful in helping us to, like I said, determine all the possible outcomes of a particular probability experiment. And in order to compute probabilities, you need to know what the sample space is and how many items are in the sample space. Okay. A tree diagram is a diagram consisting of branches corresponding to the outcomes of two or more probability experiments that are done in sequence. When constructing a tree diagram, we use branches emanating from a single point to show the outcomes for the first experiment, and then add the outcomes for the second experiment using branches emanating from each branch that was used for the first experiment, et cetera, et cetera, et cetera. The more outcomes you have or experiments you have in sequence with one another, the larger your tree diagram becomes, and the more tedious it becomes to draw. And it can get out of hand very quickly, consuming all of your paper, and to the point whereby you have no room to even fit any more branches. So tree diagrams are okay as long as you keep it down to about two, no more than three possible experiments in sequence. All right, example one, use a tree diagram to find the sample space for the sexes of 3 children in a family. Okay. Well, these tree diagrams that your author builds in your textbook start at the left and basically move to the right. Some tree diagrams are tree diagrams where they start from the top and move downward. It just depends what textbook you're looking at here. All right, so the first child, we could have either a boy or a girl. Second child, we could have a boy or a girl. And the third child, we could have a boy or a girl. All right. So when you have 3 children, the possible outcomes that could occur are discovered by following the branches of this tree. So if we follow the branch that leads to our first child as being a boy, and then follow the second branch, which leads to the second child being a boy, and follow the third branch that leads to a third child being a boy, one possible outcome would be having all boys. So boy, boy, boy. Or we could have a boy on the first child, a boy on the second child, and a girl on the third child. So we could have a boy, boy, and girl. Now, there's going to be 2 times 2 times 2, or 8 outcomes according to the fundamental principle of counting. Okay. We could have a boy on the first child, a girl on the second child, and a boy on the third child. We could have a boy, girl, boy. Or we could have a boy, girl, girl. Or we could have a girl, following this branch now, we could have a girl, boy, boy. Or we could have a girl, boy, girl. Or we could have a girl, girl, boy. Or finally a girl, girl, girl. Or a total of 8 outcomes. Okay. Does that make that tree structure make sense here? All right. So there's 8 outcomes when you have 3 children as far as their gender is concerned here. Okay. like I said, these tree structures can get out of hand very quickly. Notice this one was big enough; it consumed pretty much a whole page. But if we had like a fourth experiment in sequence, then we would have to have further branches emanating from each of these 8 branches here, and the tree would grow very, very quickly. Okay. If your tree structures are bigger than this, then you'd probably want to use a computer and program the tree structure into your computer. Computers are ideally suited for searching and sorting things by using trees. Most searches are conducted by utilizing what are called binary search trees. And those you would study, those constructs you would study in your computer science courses. Okay. But computers can move along these branches within a blink of an eye, all the branches within a fraction of a second. So it doesn't take a computer long to search out all these different possible outcomes. All right, so there's 8 outcomes there. Any questions how we got the 8 outcomes? Okay. So after we build this tree, we enumerate all of the outcomes that belong to the sample space. So all of these outcomes to the right belong to our sample space. And again, there's 8 of them. If a family has 3 children, find the probability now that they have at least one boy and one girl. Assume that each child is equally likely to be a boy or a girl. Well, at least one boy and one girl. So how many of these outcomes yield at least one boy and one girl? The first one does not. Boy, boy, boy. The second one does. At least one boy. We have 2 boys. At least one boy means you could have one boy or more boys. Same thing for at least one girl. So this has at least one boy and one girl. This has at least one boy and one girl. At least one boy and one girl. At least one boy and girl. At least one girl and boy. At least one boy and girl. And this last outcome does not illustrate having at least one boy and at least one girl. So we can see that there's 6 out of the 8 outcomes that render at least one boy and at least one girl. So the probability of when we have 3 children of having at least one boy and one girl, at least one girl, would be 6/8. Or 3/4, 4.75 or 75%. There you go. All right, here's another example. I'm using a tree diagram to compute some probabilities. A coin is flipped and then a die is rolled. Use a tree diagram to find the probability of getting heads on the coin and an even number on the die. Well, to build this tree, Liaison, it doesn't really matter what your main branches are to begin with. Notice your author chose the main first branches to represent whether we toss a head or a tail on our coin. And then emanating from each of those branches are 6 branches representing what face was rolled when we rolled the die. Okay. All right. So how many outcomes are there when you flip a coin? There's 2 outcomes. Times how many outcomes are there when you roll the die? There's 6 outcomes. So 2 times 6 is 12. According to the fundamental principle of counting, there's 12 outcomes here. You could flip a head and roll a 1. So head, comma, 1 is one output possibility. Head, comma, 2. Or you could flip ahead and roll a 3. Or a head and a 4. Head and a 5. Head and a 6. Or you could flip a tail and roll a 1. Tail, comma, 1. Or a tail, comma, 2. Tail, comma, 3. Tail, comma, 4. Tail, comma, 5, or tail, comma, 6. All right, so these are all the outcomes that could occur here. And there are 12 outcomes here. Yeah. All right, so there are 12 outcomes. And there you go. That would be the sample space consisting of those 12 outcomes here. All right, so now we can answer this question. The question is, use the tree diagram to find the probability of getting heads on the coin and an even number on a die. So what outcomes yield a head and an even number? That'd be this outcome here, this outcome here. So there's only 3 out of 12 chances of flipping a head and rolling an even number. The probability of the occurrence of that event would be 3/12, or 1/4, or 0.25, or 25%. Okay. Another way of determining the sample space is by making a table of outcomes instead of a tree structure. Consider the sample space of selecting a card from a standard deck of 52 cards. The cards are assumed to be shuffled to make sure that any selection has an equal chance of occurring. There are 4 suits: hearts, diamonds, spades, and clubs, 13 cards of each suit consisting of the denominations ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and face cards, which would be a jack, queen, and king. So that's so we have 13 cards per 4 suits. 4 times 13 is 52 cards. Okay. And here is the table that represents all the outcomes that could occur when you reach into a deck and pull out a card. There's 52 outcomes. We have 4 suits, which constitute the rows over here. And we have our cards that constitutes the columns up here. Okay. So that is a standard 52 card deck. We assume we don't have any jokers in our deck. Some decks of cards do include jokers, but those are not part of our discussion here, not a part of what we're working with right here. All right. Now we'll use this table to compute a probability. A card is drawn from an ordinary deck. Use the sample space shown in the previous slide to find the probability of getting a jack. So how many jacks are there? Of 52 cards, there are 4 jacks. A jack of hearts, a jack of diamonds, and a jack of spades, and a jack of clubs. All right. There you go. So the probability of selecting a jack would be 4 over 52 or 1/13. What's the probability of selecting 6 of clubs? Well, the 6 of clubs only occurs how many times? Only occurs once, correct? Six of clubs would be right here. So your probability would be rather minuscule. It would be 1 over 52. That makes sense here? 1 over 52. What's the probability of pulling out a 3 or a diamond? Well, how many 3s are there? How many ways can you draw a 3? There's 4 3s. And how many diamonds are there? There's 13 diamonds. Yeah. So we want to compute the probability of selecting a 3 or a diamond. Wait a minute, was that a 3 and a diamond or 3 or a diamond? Let's go back and check it out here. A 3 or a diamond. All right. Now, notice to compute the probability of selecting a 3 or a diamond, we have to count the 3 of diamond cards not once, but twice. So we count the 3 of diamonds card twice. And so therefore, how many ways can we select a 3 or a diamond? Well, how many ways can we select a 3? It'd be 4 over 52. Plus, the number of ways of selecting a diamond is not going to be 13 over 52 because we already counted the 3 of diamonds card in computing the probability of the way of computing the probability of drawing a 3 card. We already counted the 3 of diamonds, so the probability of selecting a diamond would be just 12 over 13. Would be 12 over 52. Excuse me. It's not 13 over 52. It's 12 over 52 because we already counted the 3 of diamonds. It's computing this probability. You cannot double count a card. So this gives us, or renders 16 over 52. And by 2, this reduces down to 8 over what? So it would be 8 over 26, actually. And that further reduces it down to 4 over 13. All right. So that's the probability of selecting a 3 or a diamond. Okay. All right, another example. Building a table to illustrate a sample space. Use the fundamental counting principle to calculate the number of outcomes for the experiment of rolling 2 6-sided dice. Build a table that illustrates the outcomes for that experiment until you get the same number of possibilities. Okay. Now, there's 6 different outcomes for each die. So the fundamental theorem of counting says there's going to be 6 times 6, there's 36 possible outcomes. To do that, our rows could represent the value we roll on die 1 or the red die, and the columns would represent the value we roll on the second die, which they're calling the blue die. And then to basically enumerate all of the outcomes for the sample space, we would fill out all the cells of this table here. So we could roll a 1 on a red die and a 1 on a blue die, or we could roll a 1 on a red die and a 2 on the blue die, or a 1 on a red die and a 3 on the blue die, etc., etc. So how many outcomes are possible here? Well, there's 36. 6 outcomes that could occur on the red die times 6 outcomes that could occur on the blue die. 6 times 6 renders 36 possible outcomes here. Now, we could have also built a tree to enumerate all these outcomes, but actually the tree structure would have been very tedious, and in all honesty, it would compromise the size of your paper big time. For that reason, a table is probably a nicer way to go here when rolling 2 die. All right. Table's more manageable. Okay, when 2 dice are rolled, find the probability of getting a sum of 8. So how many of these outcomes render a sum of 8? Well, a sum of 8 could occur when you roll a what? A 4 or a 4? A 5 and then a 3? Or a 6 and then a 2? Or if you roll a 3 and then a 5? Or if you roll a 2 and a 6? Those are all the ways of rolling a sum of 4 out of 52 possible outcomes. So the probability of rolling a sum of 8 rather would be 1, 2, 3, 4, 5 over 52. 5 over 52 is the probability of rolling a sum of 8. Wait a minute. Where did I get 52? I'm thinking of the card deck of the last experiment. There's 36 outcomes here, ladies and gentlemen. So there's how many ways to roll the sum of 8 again? There's all of these. All of these ways. So there'd be 5 over 36. The probability of rolling a sum of 8 would be 5/36. Okay. 5 over 36. All right. What's the probability of rolling doubles, the same number on each die? Well, how can you roll doubles? How many different ways can you roll doubles? Well, you could roll a 1 and a 1, 2 and a 2, 3 and a 3, 4 and a 4, 5 and a 5, and a 6 and a 6. Do you agree? These are all the ways of rolling doubles. So 1, 2, 3, 4, 5, 6. 6 out of 36 different ways. So 6 over 36 reduces down to 1/6. So that's about a 16% chance of rolling doubles. All right. This is making sense how we're computing these probabilities by using a table of all of our outcomes here. What's the probability of rolling a sum less than 5? How can that occur? A sum less than 5? Well, how many different ways can we roll a sum of less than 5? Let's see. Sum of less than 5 would be all of those ways there, correct? That's 1, 2, 3, 4, 5, 6 ways out of 36 possible outcomes. So your probability of rolling a sum less than 5 would be 6/36 or 1/6, or about a 16% chance. All right. Is this making any sense here? No, we're computing probabilities here by using outcomes that are either portrayed using a tree or a table. Okay. All right. Well, let's see if we can turn it over and go to our textbook and uh, have some fun here. Okay. All right. Let's see. All right. So this is coming out of 10.4. And again, if you get some time, might be helpful maybe to look through down through some of these examples here. That can help a lot. Okay. You can see some of these things are repeats that we looked at on the PowerPoint. All right. Here's a question, an interesting question. Number three, could we make a table like the ones we built in our PowerPoint for the experiment of rolling 3 dice and calculating the total? Would that be best rendered using a table or a tree? Do you think all the outcomes of rolling 3 dice?
Table, maybe?
Well, we seen where a table came in handy for rolling 2 dice, correct? There were 36 outcomes. And rolling 2 dice was conducive for a table because the rows would represent the outcome, let's say, like on die one, and the columns represented the outcome on die two. But I have a question, Lisa. If we're rolling 3 dice, though, it seems to me like we would have ordered triples, not ordered pairs. And it seems like your table would almost have to be, what, 3-dimensional. Do you agree? So let me ask you this question again. Do you think it might be easier to use a 3-dimensional table to represent all the outcomes, or maybe just use a tree structure?
Probably the tree structure.
Probably for this situation, the tree structure might be the way to go. Granted, you are going to need a fairly large size piece of paper to fit the darn tree on there. And you're probably going to have to turn your paper from, portrait view to landscape view to even have a chance. Okay. So like if you were to do that with the tree structure here, in fact, I'll get you started on this here. If we were to use a tree structure here, and a ruler comes in handy too, if you want a neat tree. So we're rolling 3 dice. Okay. Well, here we go. You're gonna have 6 branches here. And I don't know, I mean, this is going to become tedious very, very quickly here. So you're going to need 6 branches here. Is a is die 1. But then you're going to have 6 branches emanating from each of these branches. You can see how this is starting to get out of hand very quickly. But you got to have 6 coming out of this guy too. And 6 coming out of this one. And at the end of each of these, you got to have 6 more branches coming out. This is rolling. This is die 2. But then you got to have 6 branches coming out of this guy. Likewise. This is going to get out of hand. Do you agree? So you see how your tree structure lays out can become very tedious very quickly. Yeah, I mean, the tree diagram may be the way to go when you roll 3 dice, but obviously drawing it is going to be a challenge. You'd have to use some very, very wide paper this way. I mean, the dimensions of this paper would have to be very large this way. Okay. So what I'm going to do is I'll change this assignment here for your classwork number one. Suppose instead of rolling 3 dice, suppose, ladies and gentlemen, suppose that we just we flip 3 coins. Okay. So suppose we flip 3 coins or we flip 1 coin 3 times, either way. I would like you to make a tree diagram to enumerate all the possible outcomes for flipping a coin 3 times or flipping 3 coins. This one's not going to be that bad because you're only going to have 2 branches, correct? One for head, one for tail. See if you can build a tree structure enumerating all the outcomes of flipping a coin 3 times. All right. Go ahead and do that. We'll call this classwork number one. All right, so this is the tree structure that represents the outcomes of flipping a coin 3 times. Head or tail for the first flip, and each emanating from each of these main branches, there are 2 more branches representing the head or tail on the second flip, and emanating from each of these branches are 2 more branches representing the outcome on the third flip.
Excuse me.
Mm-hmm.
For some reason, I really can't see your picture is really small.
Mm-hmm. It's small. Okay, let me see what's going on here. Is that bigger now or?
No.
Well, let me try this here.
It's
You might
big
have to
enough
personally
Ryan.
in your view instead of it being on gallery, change it up to speaker.
Let me see here. It is on speaker, actually. Gallery is too small, right? And when I change it to speaker, it does get bigger on my end. It gets
I'm
huge.
saying she might have to change it from gallery to speaker on her end.
Oh, okay.
Oh, let me see. Okay.
Try that. Let's see. So what do we got here?
You can also try pinning his window so that he's the only one that shows up in the actual frame, so that way his screen is the largest at all times.
Can you tell me where I'm supposed to push for that? I'm sorry, class.
Yeah, so you'll right click on him. There'll be like 3 dots in the corner, if not, and then it'll just hit pin. So it'll be under his name. There'll be 3 dots in his upper right hand corner, and you'll click that and click pin.
Thank you. I got it.
Yep.
All right, thank you. Okay, so we can see the outcomes here. Just by following these branches, you can enumerate the outcomes. Head, head, head. Head and a head and a tail. Head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. Or tail, tail, tail. Okay. So there are 8 outcomes. And that could be determined by using their fundamental principle of counting. 2 outcomes for the first flip times 2 outcomes for the second flip times 2 outcomes for the third flip is 2 to the third power, or 8 outcomes. And your sample space would consist of all those outcomes here. You see that? 8 outcomes. All right. So I have a question for you. What would be the probability of tossing at least 1 head? Well, how many outcomes of the 8 yield at least 1 head? Well, let's see. It would be this outcome, this one, this one, this one, this one, this one, and this one. So the probability would be 7/8, correct? That's true. Okay. So, I mean, the tree structure, is still doable here. It's not, that unreasonable. Now, if I said you're flipping a coin 10 times, could you imagine trying to draw a tree structure for that? That would not be reasonable in a human sense to draw such a structure. You'd really have to turn it over to what would be called the binomial probability distribution, ladies and gentlemen, to answer probability questions for a situation like that, where you don't have to draw the tree structure for the binomial probability distribution. And we'll look at that distribution, I believe, in the near future. So, but right now, I mean, these trees are manageable. This one is still a little bit tedious, but it's still doable. Like I said, it could be a lot worse, heck of a lot worse. All right. Okay, now let's go back in our textbook. And problem number 6 here. I would like this to be a classwork problem also. Now, let's just read it. It says, we want to find a sample space for a probability experiment where a coin is flipped and a 10-sided die is rolled. So, I mean, how many outcomes are there? If you're flipping a coin, there's 2 outcomes times, and then you're rolling a 10-sided die. So there's 10 outcomes there. So there's 20 possible outcomes. All right. And you could either go by way of tree or you could go by way of table. I would like you to think about this and see if you can come up with a table that represents all 20 of these outcomes here. So let's see, ladies and gentlemen, if you can come up with a table that represents all 20 outcomes here. Okay, flipping a coin and then rolling a 10-sided die. That's the experiment. All right, so first of all, just come up with the table of the 20 outcomes, and then we can start answering some of these questions here, okay? So let's do the table first for number 6. So here's one possible way of building the table, not the only way, but um, I have the outcomes from rolling the die, 10-sided die. The rows are my outcome of flipping a coin. So you could flip ahead and roll a 1, flip ahead, roll a 2, flip ahead, roll a 3, flip ahead, roll a 4, etc., etc. flip a tail and roll a 1, tail, flip a tail and roll a 2, a tail and a 3, tail and a 4, etc., etc. All right, so there are 20 outcomes. And using this table now, ladies and gentlemen, which basically enumerates the sample space, I would like you to answer the questions, the remaining questions for problem 6 to fill out the rest of this classwork here, okay? So that's the way the table goes right there. All right. And now let's see if you can use that table to answer questions A through C there, okay? A through C. A through C. Now, what are like prime numbers? I could list the first several prime numbers. A prime number is a whole number greater than 1 that is divisible only by 1 in itself. So here's the first several prime numbers. All these numbers I'm listing are only divisible by 1 in themselves. And there's an infinite number of prime numbers, but those are the first several. That should be good enough for finishing this problem here. All right, for part A, what's the probability of flipping ahead and having and rolling an odd number on a 10-sided die? Well, that event E can occur in this number of ways here. Roll ahead in a 1, get ahead in 3, head 5, head in 7, head in 9. That occurs 5 ways out of 20 possible outcomes. So 1/4 or 0.25 is that probability, 25% chance. What's the probability of flipping ahead and rolling a prime number? Well, event E would occur 4 different ways. Ahead in 2, head in 3, head in 5, head in 7. You cannot use head in 9 because 9 is not a prime number. 9 is divisible by 3 in addition to 1 in itself. So the probability of flipping ahead and rolling a prime number would be 4 ways of event E occurring divided by 20 ways for the sample space to occur. 4 to 20 is 1/5 or 0.20. All right. Are we getting these probabilities? Is making any sense here? All right, ladies, I'm using this same sample space, the same table. I want you now to add on to that classwork by doing number 7, A, B, and C. Let's do this one now. Just add this as part of your classwork. Okay, number 7, the probability that we flip a tail and roll a number greater than 1 could occur 9 different ways. Tail 2, tail 3, 4, 5, 6, 7, 8, 9, or 10. 9/20 would be the probability, or 0.45. What's the probability of flipping a head for B and also tossing or rolling a even number? That could occur 5 ways. Head 2, head 4, head 6, head 8, head 10. Yeah. So 5/20, or 1/4, or 25% chance, 0.25. All right, making sense here? And then finally, what's the probability of flipping a tail and rolling a number divisible by 3? The only numbers in this sample space that are divisible by 3 are going to be 3, 6, and 9. So there's 3 ways of flipping a tail and rolling a number divisible by 3 out of 20 outcomes, or 0.15. Okay. All righty. All right, now.
On the other side,
What's that?
would you flip it back on the other side? Um, okay. Okay.
Am I making any sense?
Yeah.
Number 14, you can do this one for classwork. And I don't care if you build a tree or make a table. It's up to you. I'll leave that up to you. Akira wants to purchase that all-important first new car and can select one option from each category. The car models are a Ford Fusion, Honda Civic, and a Toyota Corolla. The engine type is a hybrid or an E85. The color is burnt copper, cobalt blue, or metallic green. So, ladies and gentlemen, either make a table or a tree, or draw a tree structure to enumerate all the possible combinations or outcomes. And then you can answer these questions here, compute these probabilities, A through E, okay? So number 14, go to it. Again, you can either make a table or you can make a tree structure. That's up to you, okay? Actually, I'm thinking about it here, and let's see. Which way do you think might be a little bit, maybe a little easier, in all honesty? Tree or table?
Table.
You want to make a table, you can. How many outcomes are there going to be? You got 3 models times 2 different engine types times 3 different colors. 3 times 2 is 6 times 3. There's going to be 18 outcomes. Do you agree? 18 different outcomes. All right, go ahead and do that and see if you can answer these probability questions, A through E. All right, so I decided to go with a tree structure, as I wanted. You can see that's a little bit tedious to draw this, but I do have 18 outcomes there. My three main branches are Ford, Honda, and Toyota. I abbreviated some of these things here. This is hybrid E85, burnt copper, cobalt blue, metallic green. So I did, abbreviate some of these things, and you ultimately do get 18 outcomes here. Where
Can you
the
move it up a little? Sorry.
like
Can you
this,
move it up a little?
like this.
Oh, no, I meant up,
No,
up
the other way,
along.
like that.
Yeah.
Okay, was that
Yeah,
good?
thanks.
Okay,
Yeah, that's good.
I'll let you look at that for a minute or so. Take all that in. Those are the 18 outcomes. Make sure you have all the outcomes, whether you did a table or a tree. All right, are we getting all these 18 outcomes here? Once you get the outcomes, answering the questions is pretty simple. So the first question is, what's the probability that we randomly select a vehicle that has an E85 engine? Well, how many of these have E85 engines? Well, you just got to look at the middle entry here and count the number of E85s you see. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of 18 vehicles have an E85 engine. 9 of the 18 combinations. And 9/18 would be what? 1/2, correct? So that's the probability of selecting a vehicle and it having an E85 engine. It's 9/18. What's the probability of selecting a burnt copper Ford? Well, how many Fords are burnt copper? Here's a Ford burnt copper. And here's a Ford burnt copper. So 2 outcomes out of 18 outcomes. 2/18, 1/9 is the probability of selecting a Ford with burnt copper. Probability of selecting a metallic green Honda. Well, how many metallic green Hondas do you got? Hondas, metallic green. Honda, metallic green. Again, 2 out of 18. 1/9. What's the probability of selecting a vehicle that is cobalt blue? Count how many cobalt blues you have of the 18. There's 1, 2, 3, 4, 5, 6. 6 cobalt blues out of 18. 6/18 or 1/3. About a 33% chance. Finally, was probably selecting a Toyota and it being metallic green, or a Toyota that has a copper burnt finish on it. So Toyota metallic green, Toyota burnt copper. So here's all your Toyotas down here. Toyota burnt copper, 1. Toyota burnt copper, 2. There's 2. Or Toyota metallic green, there's 1. And Toyota metallic green, there's 2. So there's 4 total Toyota burnt copper and metallic green. So 1, 2, 3, 4. So 4 18ths, 2 9ths. All right. All right. So are we did we have any success here today on any of these problems? All right, ladies and gentlemen, that is it for this section.